This is the first year algebra-based physics course. Topic 2 is one-dimensional kinematics. This section is about turning the real world into a physics problem. For a subtitle, you might say we're going to be talking about two ways to handle a physics problem. Either you can think about it, or you can use an equation. And what you're going to find is that if you think about it, you'll be able to figure out what the equation should be. And in the end, when we get to more difficult problems, it's going to be much, much simpler just to go straight to the reference tables and use an equation. But at the same time, it's very important that you understand that these equations are coming from thinking about the real world and figuring out what the equation should be. What's going to be happening in this video, we'll be presented with some very simple questions in physics. We're going to think about the problems and come up with an answer, right, a correct answer. And then we're going to see that the equation, the correct equation, which comes from thinking about the problem, gives you the same correct answer. So we're going to learn how to turn the real world into a physics problem. Thinking about a problem doesn't mean that you're not writing. As a matter of fact, the best physics students use number lines, graphs, sketches, diagrams, charts to help them to figure out difficult problems. Now, for example, on a number line, if you know the velocity is 2 meters per second, then you know that after the first second, the person has traveled 2 meters. And after 3 seconds, the person has traveled 6 meters. So as soon as you put distance and time correctly together on a number line, you're basically defining a specific speed. In other words, this number line now defines a specific speed. Here's a little sketch. All right, we've got a cliff like a mountain, and the car is driving off the mountain. Don't do this at home. You've got a height, you've got a certain distance. All right, so you've drawn what's happening in the real world, and it makes it much easier to figure out the physics problem. Graphs are also very, very helpful. Now here we have a chart. We know that the acceleration is 3 meters per second squared. What that really means is that the velocity is changing 3 meters per second per second. So the velocity is either going up or down 3 every second. So if we start at a velocity of 0, then after the first second, the velocity could have gone up to 3 meters per second. And after the next second, the velocity has gone up to 6 meters per second. All right, so it's a lot easier to figure out problems if you start trying to make little sketches of number lines, graphs, diagrams, pictures, label them. Make sure you label your diagrams, all right, charts, all right, whatever it takes to figure out your physics problem. Prior knowledge you should have coming into this video would be the basic kinematic physical quantities, which ones are scalars, which ones are vectors. So, coming in, you should know that time is symbolized T, the unit is second. That distance is symbolized D, the unit is meter. Distance and displacement are a scalar vector pair. The symbols are the same. The symbol for displacement is D, the unit is the meter. Speed and velocity are another scalar vector pair. The symbol for speed is V, the unit is meters per second. The symbol for velocity is V, the unit is also meters per second. And velocity has a vector buddy down here. He's all by himself. Here's acceleration. The symbol for acceleration is A, and the unit is meters per second squared. So again, coming into this video, you should know these basic kinematic physical quantities, whether they're scalars or vectors, the symbols, and the units. Also keep in mind, never ever change from lowercase to capital letters. Capital letters would mean different things. Other prior knowledge that you need coming into this video, from the last page of your New York State Physics reference tables, you can look them up online and download them, 6 pages. The velocity equation is the first equation on the last page, the mechanics page. Average speed or average velocity. All right, average speed would be total distance divided by total time. Average velocity would be displacement divided by time. Now, the other equation that you need to know coming into this video is the acceleration equation. Now, on the last page of the reference tables, it's written A equals delta V over T. Now, basically, I never, ever want to see you copy this from the reference tables. Always convert delta V into V final minus V initial. Right? You're not going to use this version. You're always going to use this version of the acceleration equation. So always copy, always convert the delta V into V final minus V initial. For the first 5 problems, we're going to keep the directions very, very simple. So what I'll say is this. If you have only one direction for all of the vectors, the displacement, the velocity, the acceleration, if they're mentioned, they're all in the same direction. If you're traveling in a straight line, you're not turning, and you're not slowing down. That means that you don't have to worry about positive and negative when you start plugging into the equations. So we're not going to worry about positive and negative when we plug into the equation. But I will be able to state both the speed and the velocity at the end of each problem because the magnitudes, the numbers, will be the same. All right, so our first problem. A dog runs 20 meters west in 4 seconds. How fast was the dog running? When they ask how fast, they want to know either the dog's speed or the dog's velocity. All right, so let's calculate the speed right here. Now, let's think about the problem. We know that the unit for speed is meters per second. Now that means that you're dividing, right? In order to get that unit, you're going to have to divide. And you know that that division sign, when you see that division sign there, it means per. All right? So what they're really saying when they're asking about how fast, when they're asking about the speed, how many meters does the dog average per each 1 second? That's what the speed is. Now, we've got a number line here to help us out. All right, again, use little sketches, diagrams, number lines, graphs, all right, whatever it takes to help you think about the problems. All right, so here we have a number line. We've got distance on top. We've got time on the bottom. So for time, I just put 1, 2, 3, 4, 5. And what I'd like you to focus in on is the fact that they told us that the 20 meters corresponds to 4 seconds. So what that means, if the dog covered 20 meters in 4 seconds, we can reason that the dog covered approximately 10 meters in 2 seconds, and we can further reason that the dog covered approximately 5 meters in 1 second. All right, so the dog's speed is 5 meters per second. Now, what you're really doing here is saying the distance divided by the time, the total distance divided by the time. 20 divided by 4 is giving us a speed of 5 meters per each 1 second. So we know that the speed is 5 meters per second. And since we're only going in one direction here, our velocity is also 5 meters per second, but we would say west, right? Or you could say negative 5 meters per second. Remember, never say negative, all right, and west. The negative and the west would cancel each other, and that would be wrong. All right, so we calculated in our head, we calculated the average speed. We know that the average velocity is the same magnitude, so we just stick in the direction and we're fine. All right, now, if we want to do this as an equation, all right, first of all, the line here means average. So we're going to calculate the average speed. We go to your reference tables, the very first equation on the mechanics page. Average speed equals total distance divided by total time. So you're doing the same thing here, 20 divided by 4, that you did when you were kind of just thinking about it. All right, 20 divided by 4. So the equation comes from thinking about the real world. All right, and what we get here is that the average speed is 5 meters per second. Again, because we're only going in one direction, we're not changing direction, we're in a straight line, we're not slowing down. All right, we have only one direction that we're talking about. So that means that the velocity is the same magnitude, all right, 5 meters per second west or negative 5 meters per second. All right, so what we see here is that we think about the problem, we get what we think the answer is. Then when we do the equation, right, we realize that the equation comes from thinking about the problem in the real world. All right, so you've got a problem, you think about it, you translate it into some pictures and your common sense, and then that common sense becomes an equation. And you're like, wow, we're getting the same answer. Whether we think about it logically, right, or we use an equation, we're going to get the same answer. Just a little summary of some of the things we learned from doing the first problem. First of all, the dog's distance that he covered was 20 meters. The displacement was 20 meters west. His average speed was 5 meters per second. His average velocity would be 5 meters per second west or negative 5 meters per second. Now, if the dog was running at a constant speed or a constant velocity, then we know that the acceleration was 0 meters per second squared. We derived, or we figured out, that an appropriate equation would be to calculate the speed, take the distance, and divide it by the time. Now, if you check on the mechanics page of your reference tables, you'll see that the first equation there says exactly the same thing. If you want to figure out the speed, you take the distance and divide by the time. I'd also like you to take a quick look at the second equation, all right, on that reference table. A equals delta V over T, and we know that we're not going to write delta V. We're going to write instead V final minus V initial. Finally, just a word quickly about directions, which we will get into in much more detail in later physics videos where the problems are more difficult. But for now, the positive directions, right, east, north, up, and counterclockwise. The negative directions, left, west, south, down, and clockwise. Now, you do not need to use positive or negative in an equation as long as the object is traveling in a straight line, it is not slowing down, and it is not changing direction. Problem number 2. A woman runs at 3 meters per second north, that's her speed, for 6 seconds. How far did she go? So they're asking us for her distance or her displacement. Now, we know that her speed is 3 meters per second. That means she's going 3 meters per every 1 second. If we were to put this on a number line, she went 3 meters in the first second. That means in 2 seconds she would have gone 6 meters. All right, every additional second she goes another 3 meters. All right, so here she's gone 9 meters. Here she's gone 12 meters. Here she's gone 15 meters. So for the time that they're asking us about, in 6 seconds, how far has she gone? She's gone 18 meters in 6 seconds. All right, at this rate of speed, she's gone 18 meters in 6 seconds. Now, what you can see that we did was we took the 3 meters per second, 3 meters, all right, each second, and multiplied that by the time. We took the speed and multiplied it by the time. and we got a distance of 18 meters. Now you could say her displacement would be 18 meters north or positive 18 meters. Right there. Okay? Now, keep in mind again, what did we do? We took her speed, 3, multiplied it by the seconds, right, and came up with 18. So we know that the equation must be, take her speed, multiply by the time, and you will get the distance that she covered. The speed is 3 meters per second. The time is 3 seconds. Those seconds are over 1. Seconds on the bottom, seconds on top cancel out, and we're left with 18 meters. Okay? And again, the distance would be 18 meters over here. The displacement would be 18 meters north or positive 18 meters. Whether you think about it, use scrap paper, number line, graph, whatever, okay, or you use an equation, you're going to get the same correct answer. And whatever math you do in your head when you're thinking about it, you're really doing the same math in the equation. The equation is derived from the logical way to figure out the problem from the real world. Problem number 3. A car is driving at a speed of 15 meters per second. How long does it take the car to cover 60 meters? So the car's speed is 15 meters per each 1 second. Right, that's 15 meters per second. That's what it means. Right, every second the car covers, every 1 second that goes by, the car covers another 15 meters. So we can do this on a number line. Right, so the car covers 15 meters in 1 second. That means in 2 seconds, the car would cover 30 meters. In 3 seconds, the car would cover 45 meters. All right, and to go 60 meters, all right, which would be our next 15-meter increment, to go 60 meters would obviously take 4 seconds. All right, so we know the answer is 4 seconds. So what we see that we should do here to get the answer is you take your 60 meters and you divide it by 15 meters per second, and you get 4 seconds. So you take your distance, you divide it by your velocity or your speed, and you get the amount of time. And the amount of time is 4 seconds. Now, of course, time is a scalar, so we really don't worry about direction at all. All right, so over here, the equation comes from the logic, comes from thinking about the problem. The distance is 60 meters, divide by the velocity, 15 meters per second, and you find that it takes the car 4 seconds at this speed to cover that distance. We need to understand what the unit for acceleration means so that we can think about what happens to your speed and your distance and your time when you accelerate. All right, so let's take a look at the unit for acceleration. Analyzing the unit for acceleration, what does it mean? Well, the unit is meters per second per second. So it would look like this, meters per second, that's the unit for velocity, per second. That's the unit for time. So you see that since the unit on top is meters per second, acceleration is telling us how quickly a velocity is changing, or how quickly a speed is changing, to keep it simple. All right, so let's see how the unit meters per second becomes meters per second squared, which is what you'll be seeing 99% of the time. All right, so meters per second. Well, we want to simplify this. So on the bottom, we invert, right? We invert the seconds. Now, that's 1 over seconds. So we're going to multiply top and bottom by 1 over seconds. These are going to cancel, top and bottom. And here we get meters per second squared. All right, so you see meters per second is really the same as meters per second squared. Okay, it's a simple simplification to get from here to there. So an acceleration of 2 meters per second squared means the velocity of an object is changing by 2 meters per second every 1 second. That's 2 meters per second per each 1 second, which is 2 meters per second squared. Now, it might be going up 2 meters per second every second, or the velocity might be going down 2 meters per second every second. We'll get into that in other problems. Okay, so just for a quick example, how to think about problems involving acceleration. If the acceleration is 2 meters per second squared, again, that means that the velocity changes, right? I'll put it here for just a second, right? 2 meters per second squared means that the velocity changes 2 meters per second every 1 second. So the velocity is either going up or down by 2 meters per second every second. All right, let's look at some simple examples just really quickly to get an idea of how acceleration affects velocity. If your initial velocity is 0, at the beginning, at time 0, your velocity is 0. You now experience an acceleration of 2 meters per second per second. So after 1 second, your velocity is now 2. After 2 seconds, your velocity would be 4. After 3 seconds, your velocity would be 6. And after 4 seconds, your velocity would be 8 meters per second. So your velocity is changing. Here, you're starting with an initial velocity of 12 meters per second east. Your acceleration is also east. Your velocity is changing by 2 meters per second every second. They're both east, so they're working together. So your velocity is going to increase by 2 meters per second every second. So in the beginning it's 12. After 1 second, your velocity is 14. You see where this is going. After 2 seconds, your velocity is 16. After 3 seconds, your velocity would be 18. And after 4 seconds, your velocity would be 20. Again, both east, they're going to work together. You're going to go faster. 12, 14, 16, 18, your velocity is increasing. Now here, you've got an initial velocity of 12 meters per second east, but your acceleration is west. They're working against each other, so initially, you're going to slow down. So let's see what happens. You're going to slow down by 2 meters per second every second. If your initial velocity is 12, after 1 second, your velocity is now only 10. After 2 seconds, your velocity is 8. After 3 seconds, your velocity is 6. After 4 seconds, your velocity is 4. All right? So again, the acceleration is telling you how fast your velocity is changing. And the unit shows that. Problem number 4. Now this problem is a tiny bit more difficult because we're introducing acceleration. So there's going to be an extra variable that wasn't in the first 3 problems. So, Sanaya's motorcycle is parked in front of Dunkin' Donuts. She purchases coffee for her mom and donuts for the whole family. Yum! She starts up the bike and accelerates at a rate of 3 meters per second squared to the south. What is her final velocity after 3 seconds? So how fast is she going after 3 seconds? Now, the first thing we want to do to think about this problem is think about what does acceleration mean? Well, an acceleration of 3 meters per second squared means that the velocity is changing 3 meters per second per each 1 second. All right, so in this case, because she's starting from rest, her velocity is increasing. So it's going to increase 3 meters per second every second. All right, now, you can do a number line, you can do a chart. you could have also done a chart in the first three problems. All right, I mean, really, the chart is just a number line, but vertical. All right, so her velocity is going to change 3 by 3 every 1 second. So at 1 second, if her velocity starts at 0, all right, she's parked. All right, she starts up the motorcycle. So she's starting from a velocity of 0. So this is 0. After 1 second, her velocity is 3 meters per second. After 2 seconds, her velocity would be 6 meters per second. After 3 seconds, which is the question, right? That's one of the questions. After 3 seconds, her velocity would be 9 meters per second, right? After 4 seconds, her velocity would be 12 meters per second. And after 5 seconds, which is the other part of the question, her velocity would be 15 meters per second. You see, what the acceleration means is that her velocity changes by 3 meters per second per every second. And meters per second divided by second gives you the unit meters per second squared. That's the unit for acceleration. All right, on a chart, if you want to do it this way, all right, after 2 seconds, her velocity is 6. After 3 seconds, her velocity is 9. After 4 seconds, her velocity is 12. After 5 seconds, her velocity is 15. Again, meters per second. Here's your answers here. Here's what you started with. This is the acceleration. All right, here's your answers. After 3 seconds, this would be her speed. After 5 seconds, this would be her speed. All right, now, in order to use an equation, we want to look at what we did to arrive at these answers of 9 and 15. Okay, what we did was we took the acceleration 3 and multiplied by the time 3 to get the final velocity 9. We took the acceleration 3 multiplied by the amount of time 5 to get the final velocity 15. So you take the acceleration and multiply by the time. The equation is going to have some portion where we take the acceleration and multiply by the time. All right? So let's see what we've got here. All right? Now, this is the equation that we copied from the reference tables, but we don't put triangle V. We do not put delta V. You immediately substitute for delta V, V final minus V initial. Okay, really, you're never going to write this down. What you're going to do is as soon as you want to copy that equation, A equals delta V divided by T, you're immediately going to write down A equals V final minus V initial divided by T. All right, you're never going to write that delta V. It's basically useless for you. All right, now, we're trying to find the final velocity. All right, so we got to get this by itself. All right, let's put the A over 1, and let's start by cross-multiplying. So V final minus V initial times 1. All right, V final minus V initial, all right, times 1 equals A times T. Now, there's your A times T right away. Okay, now, you want V final by itself, so add V initial to both sides. All right, add V initial to both sides. These cancel. And the equation that you're getting, V final equals V initial plus AT. V final equals V initial plus AT. All right, this is the equation that we're going to be using to find the final velocity after a certain amount of time. So let's take that equation, all right, and move it up here. All right, V final equals V initial plus AT. Now keep in mind, in this problem, the initial velocity was 0. All right, so really, it's just V final equals A times T. All right, so let's get it down to that. All right, V final equals A times T. All right, so our first problem, all right, we had 3 meters per second squared for 3 seconds. So it was 3 meters per second squared for 3 seconds. All right, we've got seconds basically over 1. So this seconds cancels one of those. And your first answer, the final velocity, is 3 times 3, all right, 9 meters per second. Now, that's your final speed, 9 meters per second. If you want your final velocity, it would be 9 meters per second south, all right? So your final velocity would be 9 meters per second south, okay? Or, because south is negative, negative 9 meters per second. All right, so this is your, again, because you're only going in one direction, you're not slowing down, you're not changing direction, there's nothing crazy going on here. Straight line, all right? Your final speed is 9 meters per second. Your final velocity would be 9 meters per second south or negative 9 meters per second. Now, the second problem, if it was 5 seconds, if you accelerated for 5 seconds, you would be going faster. All right, instead of 9, it's going to come out to 15, which is faster. All right, so what you would have here is 3 times 5. All right, your final speed would be 15 meters per second. Your final velocity in that case would be 15 meters per second south or negative 15 meters per second. Okay, so, all right, again, whether you think about it logically or you use the equation, you're going to get the same correct answer. And the equation comes from your logical thinking. So here we have another fine physics problem. Kai is driving at 4 meters per second west on the entrance ramp to the parkway when she begins to accelerate at a rate of 2 meters per second squared west. What is her final velocity after 3 seconds and after 5 seconds? Now, you want to notice right away that we don't have a problem with directions because everything is the same direction. Her initial velocity, she's driving west, and her acceleration is also to the west. All right, because we only have one direction that we're talking about for all of our vectors, right, we're not going to worry about positives and negatives when we get to the equation. All right, that makes the problem a little bit simpler. The first time we come across a problem where, for example, the initial velocity is east and the acceleration is west, we're going to have to start to be a lot more careful about putting positives and negatives into the equation. All right, here we go. First, you want to think about what does acceleration mean? All right, an acceleration of 2 meters per second squared, that's 2 meters per second per each 1 second, means that the velocity is changing 2 meters per second every second. Now, your initial velocity was not 0 in this case. She was already driving when she started to accelerate. She did not start from rest. Her initial velocity is not 0. So she's starting at a velocity of 4 meters per second. She's accelerating, right, in the same direction, so her velocity is increasing by 2 every second. All right, so we're not starting at 0 this time. We're starting at 4 meters per second. So after 1 second, her velocity has increased by 2. So after 1 second, her new velocity is 6 meters per second. After 2 seconds, it has increased another 2. So now her velocity is 8 meters per second. And after 3 seconds, her velocity would be 10 meters per second. All right, starting with a velocity of 4, her velocity is increasing by 2 each second. So after 4 seconds, her velocity would be 12. All right, and after 5 seconds, her velocity would be 14 meters per second. Whether you do it horizontally or vertically, doesn't matter, right? It doesn't matter whether it's kind of like a number line or kind of like a chart, same difference, right? If you start at a velocity of 4, after 1 second, her velocity would be 6 meters per second. After 2 seconds, her velocity would be 8 meters per second. After 3 seconds, that's the question that we're trying to answer, right? After 3 seconds, her velocity would be 10 meters per second. After 4 seconds, her velocity would be 12 meters per second. And after 5 seconds, her velocity would be 14 meters per second. Okay? Not that difficult a problem to think about. We've got some nice answers here. Let's see what happens when we plug into an appropriate equation. So, we know that the final velocity is equal to the initial velocity plus a times t. All right? We got our answer 10 here by starting with a velocity of 4. Right? Start at 4, and then you're going to add 2 times 3. You're going to add the acceleration times the time. All right, which would be 6. So it's going to be 4 plus 6. That's how you got the answer 10. For this one here, you started with a velocity, initial velocity of 4 plus a times t. 2 times 5 is 10. 4 plus 10, the answer is 14. So you see, whether you think about it logically or you use the equation, you're doing the same math. The difference is you're doing the math in your head, right, or doing it on your fingers, or doing it on a chart, whatever is the easiest way for you to get that thinking about it, okay? And then with the equation, you're doing the math on paper. You're writing everything down. So my initial velocity was 4 meters per second. And what you're doing is adding to that the acceleration for a certain amount of time. An acceleration of 2 meters per second squared for 3 seconds gives us 4 plus 6. The final velocity is 10 meters per second. If you want to do the math for 5 seconds, the only thing that's changing, right, is that it's 5 seconds instead of 3 seconds. So what you've got is 4 plus 10, or 14 meters per second. Now, since everything is going in the same direction, everything is west, everything is negative, right? The answer, if you want to know the final velocity as opposed to the final speed, I mean, technically, we were talking about final speeds here. We didn't really mention the direction. So the final speed, right, would be 14 meters per second. All right, the final velocity, right, in this case, would be 14 meters per second south. Okay, or, because south is negative, negative 14 meters per second. Okay, so technically this is the final speed, 14 meters per second. This is the final velocity, 14 meters per second south, or negative 14 meters per second. For the previous problem, it would have been 10, right? So it would have been 10 meters per second south, or negative 10 meters per second. All right, so not too bad. This is our last problem, and it has a tricky little switch up, right, that wasn't there in the first 5, so we're going to be a little bit careful here. Here we go. So Hassan is driving east on Elmont Road at a velocity of 12 meters per second. He sees a red light way ahead. He puts his foot on the brake, which causes the car to begin to accelerate to the west at 2 meters per second squared. So you notice right away, you've got an initial velocity to the east, your acceleration is to the west. So you have to start paying attention to positives and negatives, right, when you think about the problem and when you start plugging into the equation. All right, so here we go. Let's think about it first. We're starting at a velocity of 12 meters per second to the east. Now, if your acceleration is to the west, they're working against each other. The car is trying to go east. You're putting on the brake. You're accelerating to the west. All right? In other words, you could say you're decelerating. All right? But in any case, the car is going to start to slow down. And the rate at which the car slows down is 2 meters per second every second. So, after 1 second on the 5, the car is now 2 meters per second slower. The car's speed is 10 meters per second. So that would be one second later, from 6 to 5. Right? 2 seconds after the 6, All right? 2 seconds later, our speed is now 8 meters per second. Okay? And you go back another second, and your speed is 6 meters per second. After 4 seconds have gone by, so from 6 to 5, 5 to 4, 4 to 3, 3 to 2, after 4 seconds have gone by, your speed, right, is now 4 meters per second. All right, and you can say that your velocity is 4 meters per second to the east. All right, now you keep slowing down. Your foot is still on the brake. After another second goes by, and sometimes jumps like this, sometimes jumps are a great visual way to keep track of what's going on. So after another second goes by, your speed is now 2 meters per second. And finally, after 6 seconds have gone by, right? 1, 2, 3, 4, 5, 6 seconds. 6 jumps from 6 to 0, right? After 6 seconds have gone by, your speed is now 0. So it took 6 seconds for that car to come to a complete stop at the light. Okay? So after 4 seconds, 6 to 5 to 4 to 3, that's 4 seconds, 1, 2, 3, 4. Your speed is 4 meters per second. After 6 seconds, your speed is now 0. The car has come to rest. Okay? And again, the reason that you're slowing down is because the velocity at the beginning, the initial velocity, and the acceleration are opposite signs. They are working against each other. So you're going to, initially, you're going to slow down. The first thing that's going to happen is you're going to slow down. All right, at this point here, we get to a speed of 0. So we'll stop talking at this point. All right, now, over here, let's look at the equation. So our initial velocity was 12 meters per second. Our acceleration is 2 meters per second squared. The time is 4 seconds. But look what happens. We're getting V final equals 20 meters per second. That's faster. Something is wrong. Okay? And what's wrong is that you have to consider the directions. East is positive, west is negative. So this 2 right here, all right, what you're doing is you're adding, all right, the quantity -2 times 4. So what this really is, to make this correct, 12 minus 8. Your final velocity, after 4 seconds, your final velocity is 4 meters per second. All right, so technically that's your final speed. If you were going to write the final velocity, V final would be 4 meters per second still to the east, right? Or positive 4 meters per second. All right, now, if you accelerate in the opposite direction of your velocity for 6 seconds, what happens? 12 minus 12, okay, and your vehicle, your car, comes to rest. Your final velocity here is 0. Okay? All right, so again, the reason we started to have to worry about positives or negatives in an equation is because in the problem, we had 2 different directions that we're trying to put into the same equation. All right, so east has to be positive, west has to be negative.